It is part 2 of section 1.9, existence and uniqueness questions. Here we'll consider existence and uniqueness issues for metric transformations. Let's see this definition. A mapping T from Rn to Rn is said to be surjective or onto Rm if each B in Rm is the image of at least one X in Rn. To understand it more clearly, let's see this figure. Rn is the domain, Rm is the codomain, and range of T will be part of Rm. But when the range is same as the codomain Rm, then for any choice here B, we can find at least one X in domain such that X can be transformed to this point B. That is the case here in 1. So that in this case, the mapping T is said to be surjective or onto. Well, mapping T is said to be injective or one-to-one if each B in Rm is the image of at the most one X in Rn. That means that here there is no case such that more than one X is an XR transformed to the same being. So in this case, we say it's one-to-one. Let's see this figure here. This is range and domain, and in this figure, A and C are transformed to here 2, so it is not one-to-one. But in the right side, and for each point in range, when and only one pre-image exists, so that it is one-to-one. It's quite the same concept of one-to-one and onto that you learned from high school when you are dealing with functions. For solutions of Ax equals B, and existence is related to surjectiveness, while uniqueness is granted for injective mappings. Maybe this may be confusing at this moment, but later on it'll be quite clear. Okay, let's go to examples. T from R4 to R3 is the linear transformation whose standard metric is given in this way. So we have to see if it is one-to-one or onto. It's quite simple. Here, Ax equal B. B is chosen from Rm, and if for every choice of B, it is a solution, then that is onto. So that is here the surjectiveness, and here also if it is unique solution, then that is one-to-one. And we'll see along with this example. Okay, for this metric, now we'll check pivot positions. This is a pivot. Again, this is pivot. Again, this is pivot. Each row of the metric has a pivot, which means that when you try to solve this linear system and when you form the corresponding augmented metric, then you have a solution for any choice of this right-hand side, so that it is consistent and it is solvable for for any choice of B. So it is onto. So it is correct. And how about one-to-one? But for a choice here, you have a solution. We know that already. Now, if you try to check the number of solutions, then for this metric, you can also figure out by checking the pivot positions. This is pivot, pivot, pivot. So here, x1 and x2 and x3 and x4, these three are basic variable, but there's no pivot here, so that there's free variable. So if there is at least one free variable, then the solution is not unique. You may have infinitely many solutions because this free variable is acting like a parameter. So for any choice of x3, the parameter, that will be the solution, so that it has more than one solution. So it's not one-to-one. Okay. Okay, here T is a linear transformation from Rn to Rm with the standard metric A. Then T maps Rn onto Rm. Here we are now characterizing the concept of onto. If and only if the columns of A spans Rm, and because AX is just linear combinations of columns of A, so once the columns of A span Rm, then which means that range is the same as Rm, right? So we can easily figure out this first statement. So that is same as this one. Every row of A has a pivot position. Here in this example, every row has a pivot, so it is solvable and also onto. Ax equal b has a solution for every choice of b in Rm. So they are all equivalent. For one-to-one, now, here for one-to-one, okay, and if the columns of A are linearly independent, and when it is linearly independent, then basically every column of A is a pivot column, so there is no free variable, and so that Ax equals 0 has only the trivial solution. So they are all equivalent. So once you try to prove a given transformation, linear transformation, one-to-one or onto, then you may use one of these equivalent statements. When you try to prove, for example, onto, then you can here and reach at this statement or this one or that one. Then because they are equivalent to onto, so that eventually you prove the similarity for one-to-one, you can reach at any of these statements. Then that is the proof of the mapping to be one-to-one. Okay. Okay, let's see again this example. Tx is given here matrix multiplication, and we want to see if it is one-to-one or one-to. Again, we check pivot positions. Okay, this is a pivot, this is pivot, pivot is echelon form and pivot. Every row, each row has a pivot, each column has a pivot. Every row has a pivot means that for any right side B, and the augmented matrix has a solution. So existence, which means the mapping is onto. Each column has a pivot, which means that the solution must be unique because there is no free variable. Okay? So for this transformation, it's both one-to-one and one-to. Let's see another one. Now this is not in echelon form, so that from this A, let's say this is A, then from A, we have to make it in echelon form. Okay, 1 and 4 is the first column, and the 0th row, we'll move it to 0 row and move it to the bottom. Okay, so here we have 0, 0. And then we subtract and put it over there. Subtract, then that is 0. And subtract, then minus 7. Now, again, subtract, then there's a 0 and minus 4. Okay. Here now, by scaling, it can be 1. Also, it can be 1. So from here, now, again, eliminating this one, we reach at 1, 4, 0, 1, 0, 0, 0, 0. Okay, now this is an echelon form. Here we have a pivot, we have a pivot. And every column has a pivot, which means that it is one-to-one. Okay, that's one-to-one. So we check the possibility of one-to-one by using now that statement. Every column of A is a pivot column, so it is one-to-one. Now how about one-to? If you want to prove it is onto, then you have to show one of these. Here one is, every row of A has a pivot position, but this one has no pivot in third and fourth row, so that is not onto. Okay. Okay, how about this one? And this is not in echelon form. From given matrix A, we have to make it echelon form. It's 1, 0, 0, 1, and then 0, 1, 2, 3. These two rows are essentially same. Twice of this row is the same as that, so that we can reach out here by subtracting, reach out that one. Now we have this pivot, and for this one here, okay, this row has no pivot, so that it cannot be one-to-one. Also, this column, 2 columns, has no pivot, so that it cannot, okay, it cannot be one-to-one for this one, and for, because of this, it cannot be onto, right? Earlier I made a mistake. Each row has a pivot, then it is onto, but there's no pivot here, so it is not onto. Each column has a pivot, then it is one-to-one, but this two has no pivot, so it cannot be one-to-one. Okay. Now, transformation from R4 to R3, R3 is given in this way. So we need to find the transform T is one-to-one or onto. Okay, if we try to use metric technique, then from this transformation, we have to find the standard metric. Let's see what it is. Okay, the corresponding standard metric. Okay, now we have right now 4 components here. No, it's a 3 component. Okay. Okay, for first column must be action on E1. E1 means x1 is 1 and x2, 3, 4 are 0. Okay, so first column can be gotten along with x1 is 1 and everything else is 0. So it is 1. That is the first component. And that one must be 0. And again, this must be 0. How about second column? Okay, that is TE2. X2 is 1 and everything else is 0. So it's a minus 4 and x2, that is 2, and there's no x2 term, so it is 0. Now TE3, E3 is with x3 is 1 and everything else is 0. So that from the first component we have 8 and x3, okay, that is minus 8, and here there's no x3, so we have a 0 here now. TE4, E4 is with x4 becomes 1, so that we have here now 1, and that is a 3, and that is a 5. Okay, so that is the standard metric. Now let's see pivots. Here we have pivot, pivot, pivot. Okay, each row has a pivot, which means that is onto. For any right hand side will have a solution. And now how about here the columns? Okay, this one, the third column has no pivot, which means that the solution will be the number of solutions will be infinite. So it is not one-to-one. Here we have one free variable, so it's not one-to-one. Okay. By the way, here once transformation, metric transformation is given in this range, then you may think this one is the first row, because the first component, second row, third row, and collect the coefficients 1, minus 4, 8, and 1, 1, minus 4, 8, and 1. And okay, for x1 is 0, 0 to minus at 3. Okay, we have here, and there is now 0, 0, 0, 5. That is exactly this third row. You can get the standard metric in this way. Okay. Okay, now we'll go to true or false problem. Part A, mapping T, Rn to Rm is one-to-one if each vector in Rm maps onto a unique vector in Rm. Is it true? Okay. In fact, this is false. Okay, we'll see the statement after if. Okay, that portion. Okay. Now each vector in Rm here maps onto a unique vector in Rm. This part is same as the mapping to be for the mapping to be a function or transformation, so that this is not related with one-to-one or one-to. Along with that, the mapping will become a transformation, a kind of a function. So it is not necessarily true. Okay. If A is a 3x2 matrix, then the transformation cannot map R2 onto R3. Is it true? Yes, it's true. And here, now, the mapping is from R2 to R3. R3 is much larger than R2. So intuitively speaking, it cannot be onto. But here, the matrix has now 3 rows and 2 columns, something, 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 something. For this one, if we try to count the number of pivots, then maximum 2 is possible. So at least one row will not have pivot, so that it cannot be on 2. For some choice, right hand side B, it may not have a solution. Okay. If A is a 3 by 2 matrix, then the transformation cannot be 1-to-1. Okay. Here, cannot be 1-to-1. That is here again something wrong, right? And again, along with that, it can be 1-to-1. If it has 2 pivots, then it can be 1-to-1, even though it cannot be onto, it can be 1-to-1. But it says it cannot be 1-to-1, so this statement is wrong. Okay? The linear transformation T, Rn to Rm, is completely determined by its action on the columns of the n by n identity matrix. Is it true? Yeah, it is true. The columns of n by n identity matrix is basically they are E1, E2, E3, and linear transformation defined in Rn can be decided here. Okay, so we already learned this one from in the beginning of this section, and that is TE1 and TE2, so that the collection of actions on the standard basis. So it is decided by its action on the columns of the identity matrix. Okay, so it is true. Okay, this is the end of the section. Thank you.